feel they on the out and out, preaching words and verbs and academic sermons. Come along with me, take my hand and do some learning.
Welcome. Let's do some math. Today we'll talk about category theory, which is a way to generalize many of the important properties of mathematics and see how different areas of math individually share these properties. Let's get started. One way to think about category theory is it collectively generalizes many of the fundamental properties of mathematics. You will look at, let's say, topology, and notice that going between one space, say a torus, and a coffee mug, with some map, H, we may see an explicit property occur in that case. Then in algebra, you may see another space, let's say the dihedral group, on 5 vertices, and then a vector space and a map between them. You may notice some other property that's similar to the one you noticed in topology. What category theory does is it says there's a way to often connect the properties of one area, say topology, with another one, say abstract algebra. That there's a property essentially that 2 or 3 or many areas of mathematics all share. And so if we talk about it once, then we can see how it fits within the individual subject area. Functors are a way to move between categories, or for now, just think of it as a way to move between subject areas while applying categorical principles. Category theory is sometimes considered a potential foundation of mathematics. If we look at a, let's say, continuum, where on one end are spicy, high-powered, very specific proofs, and on the other end are foundational proofs that really settle how we think about mathematics and how confident we are in using it, category theory is definitely more towards the foundational end. That doesn't mean we can't get some very useful things from it. It just means that it's concerned with generalizing, unifying mathematics and looking at more foundational type principles. But at the same time, category theory is also being taught in computer science classes and used in theoretical computer science. So if you're at all interested in computer science, category theory is probably right up your alley. A category, let's say C, consists of 3 things that will satisfy 2 properties. The first of these 3 things is a collection called OBJ of C of things called objects. So for starters, just think it involves objects. You need a collection of objects. Then on these objects, you want to define morphisms. If you have a pair AB of objects in C, we'll define a collection that are simply called morphisms from A to B. Another terminology for this is arrows or maps. You can think of them for the moment like functions. Functions are examples of morphisms in many cases, but morphisms are a more general thing. If we take the collection of all of these morphisms, we simply call that HOM-C. HOM for vaguely homomorphism. So we have thus far 2 collections, a collection OBJ of C and a collection HOM of C, where the C of AB is just the sub-collection of HOM, where we're looking at morphisms or arrows or maps that go from A to B. Now we have to be able to fit these morphisms together, and this should be familiar from our previous videos. There needs to be some way of taking, for any 2 morphisms, let's say a morphism from A to B and then B to C, and then fitting it to them together so you get a morphism from A to C, and this is called the composition of morphisms. So before we were composing, let's say, elements in a group, now we're composing morphisms in a category. But the idea is the same. You have 2 different morphisms, you compose them together, and then you get a third morphism. There has to be some criteria satisfied, namely, you have to have a morphism A to B and then B to C if you're going to get a morphism from A to C. So you have to end at B and then start at B here. In particular, the one on the left has to end at B, the one on the right has to start at B. For reference, we also call the object we start at the source, and the object we end at, since we're talking about arrows, we call it the target. So morphisms start at a source object and they end at a target object. Now this is the 3 things that we should have. We should have objects, we should have morphisms, and we should have this composition. As a note, the composition of, let's say, F going from A to B, and then G going from B to C, where these are our morphisms. F is a morphism from the object A to the object B. Notice we're not calling these sets because they're more general than sets. Function could be a morphism, but a morphism doesn't have to be a function. It's a more general notion. So it is really just arrow, if you will. So oftentimes it's called arrow because we're really just focusing on the fact that there is an arrow from A to B, or there is an arrow from B to C. The composition is denoted like this. It's denoted in the same way as function composition would be denoted, where notice if we take F compose G, we start with F, we go from object A to object B, and then we go from G, object B, to object C. That's denoted from starting at A, going to C, and we denote it like this, where F is the thing we start with. So we read it right to left when we do composition, just like we would with functions. Now these three things, obj of C, hom of C, which are both collections of objects, collections of morphisms, these, along with this binary operation, this way to fit morphisms together, we need them to satisfy the following two things. The first is associativity. If we have two morphisms, FA, if we have three morphisms, one F from A to B, one G, B to C, one H, C to D, where A, B, C, and D are all objects, then we should have this associativity, where notice it looks exactly like the associativity we've seen before, with the one caveat being that we're working with composition of morphisms, which is like-ish composition of functions, where we read it from the right to the left. But nonetheless, G either associates with F or G associates with H, and it should be that either way we get the same thing. Now, if we draw a diagram where we have objects A, B, C, and D as our main part of the diagram, and then out on the side B and C, if we go from A to B with F and then B to C with G, that's the same thing as going A to C via our composition rule. So our composition rule says you can combine two morphisms and get another one. So we did that here, so long as source and targets line up. Correspondingly, if we go from B to C and then C to D, first G, then H, we get the composition here. Now what this associativity says is diagrammatically, if you, let's say, work right to left and you go F first and then H, so you go green and then yellow, that should be the same as if you go red, which is composition of F and G, and then H. This circular arrow here means that this diagram is what's called commutative, or we say that the diagram commutes. That means if you start at any spot and end at any spot, following any path of arrows, you should get the same thing. So if I go from A to B to D, like this, it should be exactly the same as if I go from A to C to D, like this, and follow the arrows that way. While we're at it, I could also go A to B to C to D like this, and it should be the same as if I go A to B to C to D like this, or if I follow again A, C, D, doesn't matter. As long as I start and end at the same spot, a commutative diagram means that we get the same thing. Moving around this diagram from a starting point to an ending point is what's known colloquially as diagram chasing. Besides associativity, the composition rule for the morphisms in our supposed category must also satisfy identity. So for every morphism, let's say F going from object A to object B, where these are not sets and functions, but sets and functions can be examples of morphisms and objects. But more generally, we have just a morphism or an arrow going from object A to object B. If we have a category, it must be that there are also morphisms, let's say 1 sub A going from A to A, a 1 sub B going from B to B, such that we get this combined equality here. Diagrammatically, that means if we start at A and go to B, first via F and then via the identity morphism on B, that should be the same as if we just went from A to B via F. And alternatively, if first we followed the identity morphism from object A to object A and then used F from A to B, it should again be the same as if we just did F, which should of course be the same as this. Notice each path that we can follow from the A up here to the B here is the same as any other path that we can follow. So going F in cyan to 1B in cyan, that path is the same as just doing straight up F, which is the same as going 1A, F that way. So starting here and ending here, any path we follow should be the same, and each one of these paths has a different color as indicated up here. So let's review. A category, script C, consists of a collection of objects, a collection of morphisms, a composition of morphisms, or a way to combine two morphisms, such that they satisfy associativity of morphism composition and identity. And again, we'll remind you that A is the source and B is the target when you have a morphism F from object A to object B. Diagrammatically, if we represent composition, say we have a morphism going from A to B and then B to C, that's the same as writing it like this, where we say do F and then G, and we write it in this reverse order because of how we have typically thought of function composition. So this is a more general version of functions and function composition, but draw on that notation when you think about this. And do note also that some authors will reverse this so that the reading order is the same as the appearance order as we move through here, or the directional order. But we'll use this order perhaps because it is maybe a little more common. Now again, a commutative diagram, as I mentioned in a specific example, is following from one spot on the diagram to any other, following along the arrows, the morphisms. If you start and end in the same spot, if the diagram is commutative, every path will be the same. So if we follow the cyan path here, which I've indicated like this, that starts at object A and ends at object E. If you then follow the magenta path here, that starts at object A and ends in object E, which I've indicated here, that should be the same thing. That's what it means for a diagram to be commutative. If this diagram was not commutative, then we could not guarantee that these are the same. So we'd have to say question mark, are these equal, question mark? We wouldn't be sure. But once you have that it's commutative, boom, it's commutative. Now you can say, we know for sure, due to the commutativity of that diagram, these are equal. Now there are a number of really important fundamental categories. Here are some of them. One is set, where the objects are indeed sets. Now that will be true of everything here. Groups are also sets with extra structure. Rings are sets with extra structure. Vector spaces are sets with extra structure. That's actually two sets with extra structure. And topological spaces are sets with extra structure. Each one of these are functions that preserve the structure of whatever space or object you're looking at. Now I said earlier, it doesn't have to be that your objects are sets, and that's true. They don't have to be, and there are cases where you will want to consider them not necessarily as sets. In fact, considering them not as sets allows you to skip between different subject areas a little more easily because you're not needing to focus on the structure of the different subject areas as much. So it can be helpful to say we're not even going to worry about whether these are sets or not. They're just objects. However, these specific cases, the objects do happen to be sets. The first one, just called set in bold here, objects are sets and the morphisms are just set maps or functions. They're just functions in the honest to goodness classic sense that you've learned about functions. The category GRP, the objects are groups and the morphisms are group homomorphisms. So they're again set maps or functions, but they also preserve the structure of the groups. Remember, a group is a set with a binary operation on it, satisfying some properties, and group homomorphisms essentially preserve the structure as you move between groups with the group homomorphisms. Rings, again, set with extra structure, two extra operations, and the ring homomorphisms preserve that structure in some way. Same thing with vector spaces over field K and linear maps. And same thing with topological spaces. A topological space has certain properties, and continuous maps are such that it respects the topological structure of spaces and it somehow preserves the topological properties as you move between spaces. To reiterate, objects of categories need not be sets. So sets are collections of elements, but objects in a category don't have to have elements. They can just be letters, period. They could just be capital A. It doesn't have to be a set that has things in capital A. It can just be capital A. Also, as we mentioned, morphisms do not have to be functions. What functions do is they map elements of one set to elements of another set. So you need to say where those elements go. If A is a set that has two things in it, let's say 1 and 2, B is a set that, let's say, has X and Y, a function between sets would have to say, oh, 1 goes somewhere, maybe 1 goes to X, and then where does 2 go? Maybe 2 also goes to X. Maybe it goes to Y, or you know, it could be whatever. But you have to be able to say where the elements of the set go to. That's what a function is. But you free yourself from this when you look at morphisms. Morphisms say, we're not going to pay attention to any of this element stuff. We're just going to say, period, there's literally an arrow from A to B, which seems maybe at first glance to be utterly ridiculous. What are you talking about? Just an arrow from A to B. What does that mean? But don't let it be too complicated. It just means there is an arrow from A to B, period. You say there's a morphism F from object A to object B, there is literally an arrow there. There's nothing else to it. Later on, you can talk about properties of these arrows and how they interact, but at first blush, a morphism is simply an arrow, period. Next, let's talk about preorders. They may at first glance seem to be unrelated to categories, but there is an important way that they do relate. So let's say we have a set P, and this is a binary relation. Don't worry about what that is exactly. It just means you can relate two elements of a set in some ways. You can think of it like less than or equal to for the moment, or you can think of it like subset if you like, but just looking at two elements, and maybe there's a way to have a relationship between them where one is less than or equal to the other. Doesn't have to be that one is less than or equal to the other, but it could be. This relation, this way of relating two things in a set, is said to be a preorder if and only if you have the following two properties. Anything is related to itself, so if you have AA, that's in the binary relation, and that's true for everything in the set. Everything's related to itself in this way, or less than or equal to itself, if you will. And then there's transitivity. If you have three elements, and A is less than or equal to B, B is less than or equal to C, then A is less than or equal to C. Now, a way to think about this is like so. If you have C, and let's say B is less than or equal to it, or in some senses, B is contained in C here, and then we have A is less than or equal to B, like so, then we would say that, okay, A must be less than or equal to C just by this diagram. Kind of here, if we look at it as containment, B fits inside of C, let's say, and then A fits inside of B, well, then of course A fits inside of C. So think about less than or equal to, or maybe more accurately, think about subset or containment. From these two things, we get transitivity. Now notice that B and D could in theory, let's say, overlap, and you could have D less than C, but it's not the case that B is contained in D, nor is D contained in B. So we would not in any way relate B and D. We would not say B is less than or equal to D. We would not say that D is less than or equal to B. So if you think about less than or equal to, in the usual sense on a number line, and you think about subsets, thinking about subsets more accurately captures what a preorder is. Now, what again may seem like a detour, let's say we have a set, and we define what's called the power set, P of X. This is the collection of all subsets of X. If you have X is equal to 1, 2, 3, 4, you could have the set containing no elements, which is a subset of every set. You can have each of these subsets that contain one element. You could have each of these subsets that contain two elements. You could have each of these that contain three elements each. And then you could have the set containing all the elements, which is just the set itself. These are all the possible subsets of this set here. And if you take the collection of all of these, that itself is the power set. So if you have these elements in the set X, these are all the elements in the set power set of X. So notice that 3 is an element of X, but just 3 itself is not an element of the power set. the set containing 3 is, but just the element 3 is not an element of the power set of X. Everything that's in the power set of X is itself a set. Namely, it's a subset of X. And now, how does this relate to preorders and category theory? Well, a preorder can be put on the power set of X simply by looking at set inclusion. So if you have two sets that are, let's say, elements of the power set, we would say that A is less than or equal to B if and only if A is contained in B. For instance, we would say the set 1, 2 is less than or equal to 1, 2, 4 because, of course, 1, 2 is contained in 1, 2, 4. Diagrammatically, you can say that X contains each of these 3 element sets, and then we draw on lines to show containment. The set 1, 3 is contained in the set 1, 2, 3. The set 1, 2 is contained in the set 1, 2, 3. The set 1, 2 is contained in the set 1, 2, 4, and so on and so forth. The set 2, 3 over here is connected by this yellow line back, showing that 2, 3 is contained in 1, 2, 3, and so on and so forth. The empty set is contained in all of these sets, and if we follow the lines up, we get containment or relation by transitivity. So since 3 is contained in 3, 4, and 3, 4 is contained in 2, 3, 4, by transitivity we can say that 3 is contained in 3, 4, contained in 2, 3, 4, and hence 3 is contained in 2, 3, 4. And how does it relate to category theory? Every preorder gives rise to a category. So category theory is pretty abstract, but it's very, very cool. I hope you learned something from this video. We'll see you in the next video.